Good afternoon, everyone, and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, Sales Manager here at Burns Engineering, and presenting today will be Bill Berquist, Senior Application Engineer. Today's presentation, Identification of RTDs, Thermocouples, and Thermowells, is our latest web-based training module designed to help you better understand temperature measurement and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If this is your first time, welcome. And when you get a chance, do go check out our previous presentations on the RTDology page at burnsengineering.com or on our YouTube channel. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We do highly encourage questions, so please type them into the Q&A section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. Today's session is being recorded and we will post it on our YouTube channel, so don't worry if you miss something. Also, if we don't get to your question or you need some additional assistance, there will be contact information provided at the end of the presentation. And finally, our goal is to answer your temperature measurement questions and challenges. We've built our RTDology series around commonly asked questions and issues. However, if you have a topic you'd like to have considered, give us a call and we'll see what we can put together. So that covers the housekeeping. So without further delay, here is Bill Berquist to help guide the way in the identification of RTDs, thermocouples, and thermowells.
All right, thanks, Jeff. So I get a lot of questions from people about they need help with identifying what kind of a temperature sensor they have in their system. And there are quite a few different types, and we're going to focus today just on the resistance temperature detector, an RTD, and thermocouples. And then some of the components that are associated with those. So the whole presentation is geared around geared towards the maintenance person that needs that kind of assistance and may have been tasked with, his supervisor may have said, we have a temperature that's not working correctly or it's out. Go out on the floor and find out where it is, pull it out and find a replacement. And it may be the first time that this person has ever had to look at a temperature probe and try and identify what it is. And so that's where we're kind of geared this whole presentation around, and hopefully that's kind of what everybody's looking for. And if if you need something more in depth, feel free to plug something into the Q&A in the chat box, and we can ad lib as we go here too. So first off, I want to start out with just some terminology that gets thrown around with RTDs and thermocouples. The first being the term RTD. It's a resistance temperature detector. You may also see it referred to as a PRT, which is a platinum resistance thermometer, which is just the most common type of RTD. And then R0, which is the resistance of the RTD sensor measured at 0 degrees C. And it's a real important resistance point. It's a way to help identify the probe, and it also will tell you if it's functioning correctly or not. And then the TCR, which is temperature coefficient of resistance, sometimes it's called the alpha, and that is the rate of change of the resistance of that sensor over temperature. And then there are a couple of standards that govern RTDs. That's the two we have listed here. And then another term that comes up that gets questioned frequently is the difference between a single and a dual element. A dual element has two separate sensing elements, and they're both placed into one probe, and it's typically done so that you can run, let's say, a local indicator, and maybe the other sensing element goes off to a PLC or other type of controller or a chart recorder. There are also triple elements, which would have 3 sensors placed in one probe. So just a little point of clarification there. So the first thing Go out on the floor, find out where this part is at, and there's usually some kind of a junction box covering it. Pull the cover off, and the first thing to notice is what kind of lead wires are in it, count how many there are, and what the colors are. So for a single element RTD, we have just typically 2 red leads and 1 white. And if it's a dual element, there's going to be 6 wires, still going to have the 2 reds and a white being one sensing element, and green and black would be the other. Now there are some differences in the color coding based on manufacturers. The standards define the colors as this, but there are at least 2 or 3 manufacturers that substitute green for the yellow leads on especially on the dual elements. So that's where you're going to see kind of the biggest difference. These will just be green for several of the big instrument houses. We'll use a different color code there. And then there are some electrical tests that can be done to help identify this part. If we suspect that it's an RTD, we have 3 wires coming out of it, or we've got 6 wires coming out, we can pull that probe out of the process, stick it in an ice bath. It doesn't have to be anything real fancy, usually just some kind of an insulated container, pack it full of crushed ice and a little bit of water, because you don't want the ice floating in the water. And let it sit for a few minutes and then measure the resistance that you get from between the lead wires. And what you want to do is check between, in the case of a 3-wire system, you'd want to check between the white lead and one of the red leads. You don't want to use both of them, just one of them, and measure that resistance. And if we want to get a little more in depth, we can go ahead and compensate manually for that lead resistance. We just take just a simple ohm meter, check between the 2 red leads and measure that resistance, and then subtract that from what you measure between the white and just one of the reds. And that will give you the resistance of just this sensing element right here. It's a little resistor made out of platinum wire. So that's what you're measuring, and that's what you want to define. And now that resistance, if it's what's called a Class A sensor, should be 100 ohms plus or minus 0.06. If it's a Class B, it'll be 100 plus or minus 0.12, and that's at the ice point. Now, if you don't have an ice bath and you don't have time to go out and do all that, you can do a quick check in the field, and at room temperature, it should read about 109 ohms. And that could be, probably plus or minus half an ohm. It's pretty difficult to get a good measurement rate at, room temperature. There's so much variation in the air that and even grabbing the probe with your hand is going to cause it to warm up, which is actually another good check. You can hook your ohm meter on it and just grab the tip of it with your hand, and the resistance should start to go up as that probe warms up. Now, thermocouples, on the other hand, are going to be just a little bit different. There's just 2 wires per sensing element, and these are also color-coded based on a couple of standards. And we have, for example, this type K thermocouple has a yellow lead and a red lead. Now, if this were a dual, it would just have another set of leads that would be red and yellow. The colors are not different between a single and a dual like they are with an RTD. And the only one that does not have color codes would be the types R, S, and B. And now these are thermocouples that are made with platinum and platinum rhodium alloy leads, so they're quite expensive, and they're usually for high temperatures, so none of the colored insulations will work with them. So you're just going to see some fiberglass insulation over the leads and these little crimp-on terminals that get used. This one happens to be labeled R. I believe this is a part from, probably Marlin Manufacturing, I'd guess, that they just write what it is right on the ceramic pieces. We go over here to a type T thermocouple. We got a little different color code there. That's going to be blue and red. And if we look at the ANSI spec for color coding, the negative lead on a thermocouple is always red. And the different type thermocouples are going to have a different color on the positive lead. So a type J, for example, is going to have a white lead and a red lead. And if the colors are gone, or if it's kind of hard to tell, pull out a magnet, and if one of the two leads is highly magnetic, you can be pretty certain that it's a type J, because that one of those conductors is iron, and so it's going to be very, very magnetic. And it can be a little confused with the type K, because the negative lead, the red one, is going to be slightly magnetic. And if you have two of them side by side, it's very easy to tell, but a refrigerator magnet will actually probably just stick right on this iron lead, whereas if you stuck it on the type K, it'd probably fall off, but you'd still notice just a little bit of a tug with it. With the type T thermocouples, can't really use the magnetic trick, but one of the leads is copper, so it's going to have a very clear appearance that it's a copper lead, and the other one is going to be silver colored. And those color codes are blue and red. The type E is purple and red, and then type N is orange and red. You know, the type N is going to be very similar to the type K. You're going to have just a very slight magnetism there, and that color code is orange and red. And then some of the rest of the world uses a little different color coding, where white is the negative lead. And then we have the other colors listed here for the various base metal type thermocouples, the J, K, T, E, and the type N. Now when we get to some electrical tests for thermocouples, this is going to be just a little bit different than what's done with an RTD. We have the first test you should do is just take an ohm meter and check between the two lead wires. And you should get some continuity, probably less than an ohm, depending on if it's a whole bunch of lead wire with it, it might be slightly over an ohm. But just to see that you've got some kind of electrical continuity there. And it's just to determine that this junction right here is in fact still connected. The next test would be to determine if it's this grounded junction or ungrounded. In the grounded junctions, you're going to get continuity between the sheath of the probe and both of the lead wires, because this junction is actually welded right into the sheath of the probe. And that's an important thing to know when you're specifying a replacement thermocouple. That's something you should pass along to the manufacturer when you're requesting a replacement probe. If it's ungrounded, you're not going to get any kind of continuity between the lead wires and any part of the probe sheath. And then the parts that are common between the two types of sensors, if we look at a physical description of both of these, the first thing is if you had pulled this probe out of a Thermowell, it probably has some kind of a spring on it so that it helps seat the probe in the bottom of the Thermowell. And that's important for a couple of reasons. One is it helps with the heat transfer a little bit, and the other thing would be that if there's any vibration going on in the process, that spring loading helps prevent the probe from rattling around inside the Thermowell. So you should note what type of spring loading the temperature probe has. This first type here is a 1/2 inch NPT pipe fitting, and the spring is actually inside of it, so the probe will retract inside that fitting. A similar type is this where the spring is exposed, and this would typically be the compression on the spring would be provided by a terminal block that would push on the back of that spring right in this area, and the lead wires would come up the center of the terminal block. Another very common type is this bayonet lock fitting. These are used in like plastic extruders and some other similar types of components where there's a small fitting that's screwed into the Thermowell or the molding die, and it's just a little quarter turn lock, and so that compresses the spring and holds it in place. And then the other style is this terminal block, which is captured on a steel plate, which is attached to the temperature probe. And the spring loading is provided by these spring-loaded screws. So as you install this probe into the well bottom, or the probe bottoms out in the thermal well, and then the terminal block, as you tighten those screws, it provides the spring loading and holds the probe firmly in the bottom of the thermal well. There are some other methods there, but they're typically pretty rare. These are just some of the most common ones that are out there. And finally here, most probes will have some kind of identification on them. A lot of the RTDs will have a serial number on it. Depending on how long it's been in service, it may be difficult to read. But most manufacturers will put a serial number on it. And with that, you can usually track back, and find all the details about the probe and what it is, and they'd be able to help you further identify it. Some of the different locations with temperature probes, it's right on the sheath. If it's a large enough diameter, it would be there. Sometimes it might be back in this area where it's a little transition piece to cable. There might be some identification marks there. Some of the smaller probes, it gets really difficult to put a serial number on it, and so there's a little bit of creativity there sometimes in where it's located. Direct immersion style sensors, it might be on the non-wetted part of the sensors. This is right back on a threaded fitting, I guess, where a connection head might be mounted. And this also has, this one looks like it has a serial number and maybe some material certification heat numbers listed along with it. So, Jeff, I don't know if we have any questions yet. We could maybe take any of those if there are any right now.
Yeah, it doesn't look like we have any, but just a reminder to folks, if you do have a question, go ahead and type it into the chat section or the Q&A section on your screen, and we'll go ahead and get an answer to that. I think the other thing to mention as you're trying to identify what type of sensor you might have, obviously the thing that you would start with is if you have an actual part number someplace in your system, that helps as well. Or if there's a tag on the any place on the sensor itself or on the connection head, as much information as you can give us, that helps to identify what it is. Sometimes it might be in the case of burns, we happen to put our order number on that tag as well. So if you've got the order number, most times we can trace that back to be able to find out what that sensor was. So the key is give the manufacturer as much information as you have to help limit down what it might be that you're looking at.
Yeah, well, no, that's the easy way to do it. Anybody can do that.
Well, although we have found also sometimes as ERP systems have become popular, many part numbers, model numbers for RTDs and thermocouples can get quite lengthy. And what tends to happen is there's not room for them in the ERP system field, and numbers start to get truncated. And so then it becomes more important to have a few more identifying characteristics. If the whole part number isn't there, you might end up with something different than what you really need. So it's important to pay attention to that.
All right. So next, I want to talk about Thermowells. If you have a Thermowell and you need a replacement probe to go in it, the most important useful number is the bore depth. And this can be measured quite easily by just taking a piece of wire or even the probe that comes out of that well and just measuring this dimension that's shown here. And with this number, the probe supplier can get you the right length. And it's just really the most useful number to have.
I think one of the confusing things, and Bill go over it a little further here, is that different manufacturers have different ways of measuring the immersion and the lag lengths, and they kind of measure things a little bit differently. So if you can get that bore depth, then there's no confusion. That's kind of a universal number or universal measurement. So with that, you can be sure that you're going to get the right sensor to go into that Thermowell.
Right. Some of the other dimensions that you'll see, if you need to specify a replacement Thermowell, some of the ones that you need to look at are the immersion length, and that's this U dimension. So that's just the distance from the end of the threads here down to the tip of the well. And then again, the bore depth, these diameters, like this shows a tapered stem Thermowell, so there's going to be two diameters, one kind of the major and one at the very tip section. There are some standards there that manufacturers have, but if you need something a little different, that's usually available also. But because you want to make sure you get the same dimension well to go in so that you have the same performance out of it as you did with the original. And the other dimension is the lag extension, and that's usually indicated by the letter T. And the instrument connection thread, most of these are a 1/2-inch NPT. If it happens to be a metric, it might be like an M20 size. But these are, the kind of the critical things to measure when you're trying to specify the Thermowell. And the other thing would be to note the diameter of the probe that came out of it. Some wells, especially for thermocouple applications, may have a bore diameter that's 0.385. For most RTDs, they're a 1/4 inch, so the bore diameter is going to be 0.26. And then if you know the material of the well, that's something else that you could pass along too. So the physical description, we want to look at the process connection, whether it's a threaded or a flanged well. And then the style of the stem. This one happens to be stepped, or some call it a reduced tip. This is a tapered stem where it goes from a larger diameter down to a smaller diameter. The reduced is typically specified when you need a little faster response time, and the tapered stem is a compromise between a straight stem and the stepped. So it gives you a little more strength, but a little faster time response than if it were all a straight stem. The weld-in style Thermowells, you'll typically find those in some kind of a process tank, and it'll be welded in place. Be a little difficult to replace one of those. We don't see that too often. The other style would be socket weld, and these are typically used in a pipeline situation. They get welded into a little ASA style socket that's welded to the pipe, and then this Thermowell drops in, and you weld around the outside edge of it right back in this area here. Some other kind of less common styles would be this kind of this O-ring seal type Thermowell. It goes sometimes by the trade name Ingold. They were the company that developed it several years ago. This typically drops into a little socket in a bioreactor vessel, and you can just kind of see the little orange O-ring there that does the sealing inside a little adapter that's welded onto the tank, and then this nut holds the Thermowell into the tank. Another type of sanitary well has a hygienic ferrule on it. This happens to have a straight stem on it. Another less common type of well, a lot of times used in chemical applications, is a Van Stone. And this one installs, it has a separate backing flange that covers the back of this and gets bolted over the top of it to hold that in place and make the seal to the process. And a final type here, this is a sanitary well that has a hygienic ferrule process connection, and it also has one for the instrument connection. And this would be important to pass along. If you're trying to find a replacement temperature probe for it, it's going to have that hygienic ferrule on the temperature probe to be able to mate up with this style Thermowell. This is a little bit of a hybrid type of Thermowell where it actually replaces part of the process piping system, and then the Thermowell is contained within this elbow. We look at the cutaway here, we can see a temperature probe installed here, and the Thermowell is part of this piece of pipe, and usually it protrudes down inside here, 2, 3, maybe even 4 inches. And this one has weld ends on it as its process connection. And you may also see these with a hygienic ferrule connection. It might be a compression union or some other types, but certainly the weld-in and the hygienic ferrule are the two most common types of process connections for this style well. You're going to notice some markings on Thermowells too. Most of these are going to be the material heat numbers. And now this is what, when the parts were made, the metal chemistry is defined by these heat numbers, and they'll be marked on the part as a means of material traceability. These often are not much help to a manufacturer if you're trying to identify a Thermowell. It would just tell them, what lot of material it was made out of. So that's really not a lot of help passing those along. There may also be a tag number that could be, in this case, it looks like some kind of a stamping or etching process to put these numbers on, and that can be helpful. This one shows the actual material, 304 stainless, and a heat number. And then if there's no other way to find out, there is a method using an X-ray fluorescence gun here to determine what the material is on that Thermowell, and we could match it up potentially with that kind of a process. I suppose another potential way here is if you could determine what the material of the pipeline or the tank is, you could match it up that way too and just use the same material as the pipe or the tank. So next is connection heads. And this is going to be one of the first things you see when you go out on the floor and try to find this temperature problem that's not working for you. And these are typically all kind of covered with dust, or they're corroded, or they're, if it's been in service for a long time, it's going to look pretty rough. And you may have a little trouble taking the cover off of some of these, especially like an aluminum head, if it's seen some like caustic washings, or if it's a cast iron head, there might be some rust and stuff that's holding that cover on. They can be a little difficult to remove sometimes. But inside, you're going to see, you know, the number of lead wires and whether there's a transmitter inside. And you want to note the label on the outside of the head too to see if this is actually a hazardous atmosphere. Hopefully you know that already, but this will help identify what kind of a rating you're going to need on a replacement part. This one happens to have an FM rating, and it's a Class 1, Division 1, Group A, B, C, D. So this one would be useful in like an acetylene gas. That's kind of the most explosive atmosphere there is. And this just says FM approved. There are many, many other approvals that can be out there. This one has the same kind of a Class 1, Division 1 approval, but this one has FM, and the C is for Canada and also the US. So you could use it, or it would usually be suitable for use in either country. Different parts of the world have different requirements, so it's important to look at that label and note what it says on it, and pass that along to the manufacturer so they can help provide you with the correct parts. Now inside this head there may be, I mentioned, a transmitter like this. Certainly note that. If there are any identification marks on it, that helps to let the manufacturer identify it. Some will have an indicator. You may open it up and just find the terminal block. And also note that some indicators will have a separate transmitter to drive the display. It might be right in the connection head with the with the indicator. It may be off in a panel somewhere. And so that's something that you'd have to be aware of. There are some indicators also that are battery powered. If you're not getting a reading, it might just be a simple task of replacing the battery. And so with that, if we have any other questions here, I'm just going to go through a little summary here real quick. One of the first things you want to do, identify the lead wires, whether you've got 2, 3, 6 wires or 4. And if you can, do some electrical tests. Look at the process connection sizes and the types. I also should mention too that I did find a really good thread identification guide that Swagelok puts out, and you can just go on Google and search for that. They do a really good job of identifying all the different NPT and BSP and metric thread sizes and how they're used and what they're used for. So that's a big help in identifying what size threads your temperature probe may have on it, and also the Thermowells. And then note the spring loading style and the connection head. Look at the hazardous area ratings, if any, transmitter, local indicator type stuff. And then if all of that fails, doesn't work, take a few pictures inside the connection head, the temperature probe, maybe lay a ruler next to it. All these things will help the RTD or thermocouple supplier help identify that part for you if there's no other means to do it. So, and with that, I think we'll see if there are any questions here. And
yeah, if you do, again, if you have any questions, go ahead and type them into the chat or the Q&A section, and we'll go ahead and get an answer for you. There is one question here. In what about 2-wire RTDs? So how do you tell if you've got a 2-wire RTD or it's a thermocouple?
Well, the easiest way to do that would just be to put an ohm meter on it and measure the resistance. A lot of the 2-wire RTDs are going to be 1,000 ohms at 0 degrees C. So at room temperature, you're going to be reading about 1,090 ohms. So that would be one quick way. If the probe happens to be open circuit, that's going to be a much tougher time. Then you have to look at the leads themselves to see if those are actually the thermocouple material, like we mentioned with the some of the leads being magnetic, or one of them may be a bare copper lead that's going to have that copper color to it. It may have a different color code. A two-wire RTD would typically have a white and a red lead. That happens to be the same for type J thermocouple. So there you could use the magnet trick to see if either one of those are magnetic. If one of them is, it might be a thermocouple and not an RTD after all. So, and like I said, sometimes it just can be a bit difficult if a thing is really old and it's broken. You know, we do have a few challenges with identifying parts that have been in service for a long time.
Okay, another question there. How about, is there a way to help identify either just the difference between an RTD and a thermocouple based upon the control system or the, you know, the reading? Obviously one's voltage, one's resistance, but is it from the control system or from the card? Is there any way to determine it from, I guess, from the other end of the process?
Yeah, you might be able to go back to a you know, PLC or a transmitter and see how that part is configured. The peripheral that it's connected to may have the terminals labeled. Some have a little schematic on it that would show a you know, like a voltage change, for example, for a thermocouple, or a resistance symbol for a RTD.
Okay. Is there any way to tell by feel from the, you know, the lead wires themselves, just by feeling them, if it's a thermocouple or a RTD?
Most RTDs will have multi-stranded lead wires, and some thermocouples are going to be solid conductors, so that would be a really quick and easy kind of the feel test for those. I don't think you'd run across too many RTDs that would have solid conductor leads attached to them, so that could be a good starting point.
Okay. Well, thanks, Bill. It doesn't look like we have any other questions right now, but if in the future anybody has any questions, feel free to give Bill a call, or anyone here at Burns Engineering. We'd be happy to help you out and try to get you an answer to your question. We did just want to let you know that we do have an upcoming RTDology session on May 10th, and that's on troubleshooting RTDs and thermocouples. And also, all of our recordings are available on our YouTube channel, which if you go to YouTube and search RTDology, you will find all of our presentations and recordings on that site. So with that, we hope to see you at the next session, and thanks for joining us.